section 8.2 leading up to exercise 8b. I'll follow this section by showing you a few questions where you will be asked to find the domain and range of those functions. So here we are going to have parametric equations that are defined using trigonometric functions. So here we've got 2x is equal to sine t plus 2 and y equals to cos t minus 3. T is defined for all real values. So first step is to find the Cartesian equation. The whole idea of eliminating t is still going to be used, but the way you do it with trigonometric identities, trigonometric functions, you are going to find an identity or two identities or three identities that connect sine and cos in the first example, or any two functions that you're dealing with. So over here we've got sine and cos t. The identity connecting these two together is sine squared t plus cos squared t equals 1, always quoted. And we are going to substitute these into that identity. So rearrange first though and substitute. So we are going to rearrange these, so we've got something to substitute in here. So we want to replace sine t, and over here the same thing, we're going to replace cos t with the appropriate substitution. So sine t from the first equation can be replaced with x minus 2, and cos t, looking at the second equation, can be replaced with y plus 3. So now we're going to substitute into the identity to obtain x minus 2 squared plus y add 3 squared equals to 1. So you can see that this is circle, centered 2 minus 3, radius 1. Okay, so we can sketch it. So to sketch it for part B, we're going to go to the point 2 minus 1, so 2 minus 3 rather. Over here, that's the center. Radius is 1. Here's my circle. You may be asked to find the domain and range of these of this function. So if you are looking for the domain, obviously once you've sketched it, you can just look at the graph. So it looks like it's going to start from this point, which is 1, up to 3, including 1 and 3. Let's have a look. If you look at the actual parametric equation describing x's, what this represents is what x's are represented by is the sine graph plus 2. So if you think about the sine graph, the usual sine graph looks like this. So the lowest value is minus 1, the highest value is 1. If you shift it 2 up, you're going to shift the lowest value up to 1 and the highest value up to 3. So you'll be getting this sketch instead. So you're going to get anything between 3 and 3 is included, and 1 is included, because the only values that actually t is considered, it goes forever, so you can have all the values, yeah, but just between 1 and 3. So x is between 1 and 3, which is confirmed by looking at the graph. Now if you look at cos t, at the y, so for the range, you are going to look at the cos graph. So cos t minus 3. So if I sketch cos t, remember cos varies between minus 1 and 1, so you don't need to sketch it to know that the lowest value will go to 3 less than the lowest value for cos t. So you'll be getting minus 4, and the highest will be 3 less than the highest value. So 1 take away minus 3, which is minus 2. but we're going to sketch it. So cos graph looks like this. So the highest value is 1, the lowest value is -1. We're going to shift it 3 down, so it goes 1, 2, 3. So here's my highest value there. 1, 2, 3, here's the lowest value. And the sketch will vary between -2 and -4. So that will be our the range possible values of y between -4 and -2. Let's just double check. There is -4, there is -2. You could have got it from the Cartesian, from the looking at the graph that we sketched in part B. So let's look at example 4. Here we've got, again, two trigonometric functions describing x is sine t, describing y is sine 2t. T is restricted this time from -half of pi up to half of pi. So again, let's think, how is sine t and sine 2t connected? Is there an identity that you can think of that connects these two? Now I can think of the identity for sine 2t, the Wangle formula. That is equal to 2 sine t and cos t. And I'm very happy because I've got it in terms of sine t. So there's two functions already. And I'm really happy about having cos t, because whenever there is a sine t and cos t, they are related by sine squared t plus cos squared t equals 1, so they are interchangeable. So what are we going to do? We are going to start substituting the replacements for our functions. So the first thing we're going to do is substitute, instead of sine 2t, y, and instead of sine t can go x, and instead of cos t you can have plus or minus, because you could have either. Now cos squared t is equal to 1 minus sine squared t, so cos squared t is 1 minus x squared. Therefore cos t could be plus or minus 1 minus x squared. There you go. So this is our substitution, giving us y equals to plus or minus 2x square root of 1 minus x squared. Now I've allowed for plus or minus. It is quite possible that it is either going to be positive 2x square root of 1 minus x squared or negative 2x. So depending on our domain and range. So let's have a go at looking at those values of t and how they affect the domain. So to find the domain and therefore the values of k, we need to consider the graph x equals sine t, because we wouldn't be able to sketch this Cartesian graph, the equation from this Cartesian equation. So for the domain, we are going to think about the graph of x equals to sine t when your t is restricted from -1/2 of t up to minus pi over 2 up to pi over 2. So if I sketch it from minus pi over 2 up to pi over 2, so it's going to go, okay, so this is from -1 up to 1, if you can look at the graph. So these are your x's here, this is t's, this is the graph we are going to have, including the endpoints, so just color in the circles. So you're going to get anything from -1 up to 1. There you go. So when x is equal to, if you substitute that, that gives you k is equal to 1 for this particular question. Okay. So what about the range? So the range is of y equals sine 2t. So if I were to consider this graph, so this is between minus pi over 2 and pi over 2. So sine 2t, normally sine t would go, we reach the 1 at pi over 2 because it's squashed. That would happen at pi over 4. So you'll be getting that graph. And then you'll be getting that part. So you get the 4 period here. So the y values are between minus pi over 2 up to pi. No, the t's are between minus pi over 2 up to pi over 2. So the y values, which are on our vertical axis, are between 1 and minus 1. Now for the final question, which I think the book ignored it a little bit, so, but what is the actual equation? So do we have 2x squared of 1 minus x squared, or do we have minus 2x squared of 1 minus x squared? Now the way to consider it is to think about the signs of our functions. So when you have the values of is from 0 to pi over 2, you could see between 0 and pi over 2, our x's are always positive. So when t's are between 0 and pi over 2, x values are greater than 0. They are actually between 0 and 1, but they are positive. Positive. Now the y values, which are over here between 0 and pi over 2, are also positive. So are y. Okay. So if I have a positive value of x here, that also is always going to be positive because it's positive square root. Then y will have to be equal to 2x to remain positive, not minus 2x, because that would switch its sign to negative. So this is the one that will work for the t's between 0 and pi over 2. Now if you consider t's between minus pi over 2 and 0, you could see that it's negative, x's are negative, and y's are negative over here as well. So the only way it's going to work, if you think about it, if you try over here, so if x's are negative, y will remain negative if you don't put a minus in front of it. If you did put a minus, if your x's were negative, y's would turn into positive. So this is no good, reject this one. Obviously the book didn't really look into detail about this, but even if you don't understand it at this moment, when you finish the book, I would recommend you come back to this example and have a look at this video again, because those questions have been asked in the exam before, so you need to think about it, why this is the case. Okay, so we are going to move on to example 5, and then it's exercise 8b. So in the example 5, we've got parametric equations: x equals cot t plus 2, y equals cosec squared minus 2. T is restricted between 0 and pi. So the first thing, we've been asked to express it in y equals f of x form. So we're talking about finding Cartesian equation describing this curve. So think about trig functions. You're looking for identities connecting cot and cosec. Cot and cosec love each other. There is an identity 1 plus cot squared t is equal to cosec squared t. So as soon as you see these two together, they are like brothers. They're connected in with this identity, and we will differentiate them as well. So you can now start thinking about substituting these functions into the identity. So let's rearrange them. So rearrange. You're going to get cot t is equal to x minus 2. So that's from the first equation. And cosec squared t is equal to y plus 2. So I'm not going to square root it because our identity has squared bits. So substituting into the identity, we'll have 1 plus x minus 2 squared is equal to y plus 2. Let's make y the subject because we've been asked to make y the subject. You'll have x minus 2 squared. Take away 2 from 1 to get minus 1. So expanded or not, I think it's just perfect in this form, and especially as this one will give you the idea of the domain or range of this function as well, particularly the range. So if you just I'm tempted to draw it, so I'll sketch it here. So the minimum value is 2 minus 1. So we've got it's equal to 1. That's going to go through here. There you go. But that just tells me that there will be a limiting value of minus 1. But let's just check about the domain and then range. So the domain of this function, if t is between 0 and pi, we need to think about cot t. What is happening to cot t between t equal to 0 and pi? So if I were to sketch this graph, so remember cot is going to be having asymptotes at 0 and then pi, and it's kind of does the opposite to tan. Tan goes through 0 and goes that way. And this is pi over 2. So between 0 and pi, can you see that you are getting the whole long branch here for our values of x? So no limits whatsoever. You can get all possible values of x. So x belongs to real values. So the range, if you can either look at this one, but that's a little bit more tricky to consider that. Okay, but you can look at the range from this graph. I've sketched my quadratics. The limiting value is the minimum, which is at minus 1, and you're going to get all the values above. So the range would be y is greater or equal to minus 1. So that's the range, and that's the domain. And I've already sketched it because I couldn't resist doing it. So maybe find that point over here. So when x is equal to 0, y is going to be 4 minus 1, which is 3. There you go. That's 1. That's going to be 3. If you try to get the range from this function, it's not impossible. But Cosec, you need to think what is happening to Cosec when it's squared, and then you need to shift it to down. So that's another thing that you might want to come back at the end of the year when you've gone through the whole textbook. But Cosec, normally, if you think about what Cosec looks like, so it's normally it's just a sine graph looks like this. So the cosec has got asymptotes whenever sine hits 0. So it's over here and over here. That looks like this. Let's just draw two branches from 0 and 2 pi, although we're only interested up to pi. So, but let's say it was up to 2 pi. Now, if you square it, whether you square that or that point which was at 1, when you square it, it will remain at 1. But that point here that was at minus 1, when you square it, it will be flipped over here. So the shape of the remaining part of this curve will slightly change, but it still will go increasingly higher and higher. So you are going to get the lowest value of 1, but then we are taking away 2. So the whole thing is shifted down to 1. So this one here would be like this, from 0 to pi, and if you head to 2 pi, the same thing would be happening as well. So that is still going from minus 1 upwards, which was easier to get from the quadratic. Okay, so I think that's the last example. So you can go and complete exercise 8b.